This presentation discusses the descriptive inorganic chemistry of titanium and vanadium. Titanium has an atomic number of 22. It appears as a hard, silvery white metal and has the lowest density among the transition metals with a density of only 4.5 grams per cubic centimeter. It was discovered by William Gregor in 1791. He found a black material that is now called ilmenite and treated it with hydrochloric acid and sulfuric acid and obtained the residue of an impure oxide of what he then concluded was a new element. After 4 years, Martin Heinrich Klaproth also discovered the oxide but from a different ore named rutile. He then called the element titanium from the Titans, who were the children of the goddess Gaia, the goddess of earth, and the god Uranus, the god of heaven, in Greek mythology. Titanium is also known as a very abundant element, being 9th of all elements and 2nd of the transition metals.
Based on the graph, titanium has a higher atomic radius compared to vanadium. As the number of electrons increases, the number of protons also increases, thus, the atomic radius decreases. The enthalpy of atomization of vanadium is greater than titanium because vanadium has a stronger metal-metal bonding than titanium.
At high temperature, titanium reacts mostly with nonmetals, particularly with oxygen, which forms metal oxides, and nitrogen gas, in which the titanium burns. A special characteristic of titanium is that at room temperature, it is resistant to corrosion.
Titanium dioxide is predominant among the oxide forms of titanium. It has 3 forms, namely, rutile, anatase, and brucite. Rutile is the most common of them. In the first equation, it is shown that titanium dioxide reduces to TiO 1.985 when it is heated at high temperature in the presence of oxygen. Titanium gives numerous non-stoichiometric oxide phases, which are called Magnelli-type phases, with the formula TiNO2n-1, wherein n is greater than or equal to 4 but less than or equal to 9. Common Magnelli-type phases are Ti3O5 and Ti2O3. In the second equation, the titanium dioxide has been reduced by hydrogen gas at 900 degrees Celsius to form a blue-black metal trititanium pentoxide. Titanium 3 oxide forms by reacting titanium dioxide with titanium metal at 1600 degrees Celsius. This compound is resistant to reactions except with oxidizing acids like sulfuric acid, chromic acid, nitric acid, etc. This compound turns into a metal at 200 degrees Celsius. It is dark violet in color. Titanium 2 oxide also forms by reacting titanium dioxide and titanium metal, but at 1500 degrees Celsius. Titanium 2 oxide has a defect rock salt caused by the vacancies either in titanium or oxygen sites. Therefore, it produces a non-stoichiometric range 0.75 to 1.25. Titanium 2 oxide forms a trigonal prismatic array at 3000 degrees Celsius. Sulfides are less examined compared to oxides. The most predominant form of sulfides is titanium disulfide. Titanium disulfide forms by reacting titanium metal with sulfur at 500 degrees Celsius. Titanium disulfide reacts with oxygen upon heating to form titanium dioxide and sulfur. Titanium disulfide also reacts with water to form titanium dioxide and hydrogen sulfide. Titanium 3 sulfide also forms by heating titanium disulfide. One of the most predominant forms is tetrahalide. Titanium forms an interesting color, especially when the halide is easily oxidized. Titanium tetrachloride forms by reducing ilmenite with carbon at 950 degrees Celsius and thus producing carbon monoxide as the byproduct. Titanium tetrachloride reacts with magnesium to produce titanium metal and magnesium chloride. The magnesium reduces the chloride in this equation. Hydrolysis of titanium tetrachloride forms hydrogen chloride and titanium dioxide, which could be used in paints. Titanium tetrachloride is oxidized to produce titanium dioxide and chlorine. Titanium tetraiodide is formed by iodination of dioxide with aluminum triodide when heated at the temperature of 400 degrees Celsius. The general equation in the formation of titanium dihalide is given in equation 14. The titanium tetrahalide is reduced with titanium metal to form this black solid titanium dihalide.
Titanium metal is often used in industries such as in making aircrafts, spacecrafts, submarines, and paints. Titanium is usually in the form of alloys in which other transition metals such as vanadium, molybdenum, manganese, etc., are present in the alloy. As previously stated, titanium is resistant to corrosion at room temperature and has a low density. Thus, titanium alloys are light, strong, and very durable. Titanium alloys consist of titanium, metal and other metals which can be used for everyday applications. One special use of titanium alloy in particular is its application in spacecraft and aircraft industries. Aircrafts consist of titanium alloys which are composed of other transition metals such as iron, molybdenum, and chromium, which are used to stabilize the alloy. Submarines are made up of alloys that consist of 5% aluminum and 2.5% tin. Dental implants are made up of alloys that consist of 6% aluminum and 4% vanadium. Orthopedic implants are made up of alloys that consist of 6% aluminum, 4% vanadium, 0.25% iron, 0.2% oxygen, and the remainder is titanium. Titanium tetroxide is used in thickening latex. Titanium dioxide appears as a white powder which can be used in paints. Titanium complexes, particularly D0, are often diamagnetic. Titanium complexes undergo hydrolysis that result with OH and O bridges. Coordination number of 6 is the most common geometry of titanium 4 complexes, but coordination number of 7 and 8 are also formed. Titanium tetrahalides often form 6 coordinate in which the O or N ligands are attached to titanium. They produce yellow or red colors when the ligands are ethers, ketones, amines, nitriles, etc. Phosphorus and arsenic also complex with titanium tetrachloride, specifically as chelates. These are examples of titanium complexes that have 7 or 8 coordination numbers. Titanium complexes also react with alkoxides, titanium dichloride, dialkoxide, and hydrogen chloride. Tetraalkoxides can also form by reacting titanium tetrachloride with dry ammonia. One of the uses of organic titanates when exposed to atmosphere is that they are used in fabrics, which are water resistant, and paints. They are also used in glass. Titanium tetraalkoxides are chelated with beta-decatinates to produce products which are water-soluble and form gels which react with cellulose ether colloids to thicken latex paints. Titanium, unlike zirconium and hafnium, can easily be reduced to form trivalent state. Titanium trihalides bond with P or N ligands. Titanium-3 undergoes oxidation when exposed to atmosphere. Most geometrical arrangement of titanium-3 is octahedral by reacting e.g. titanium trichloride with excess ligands to form octahedral as secondary valence while halides as primary valence. One of the compounds of titanium-3 complexes is the one with urea ligands that bonds with oxygen atoms in titanium that are resistant in oxidation. Neutral titanium-3 complexes have ligands e.g. pyridine, acetonitrile, tetrahydrofuran. Anionic complexes can be produced by reduction reactions. For example, titanium trichloride reacts with NMe4F to produce NMe4 TiH2O 4F2 TF6 H2O. Some complexes of titanium-3 showed that its molecular geometry is non-octahedral. TiBr3 NMe3 2 has geometry of trigonal bipyramidal and TiNSIMe3 2 3 that is trigonal planar due to bulky ligands that is difficult to occupy the spacing around the titanium-3. The next element to be discussed is vanadium. In 1801, Andrés del Rio discovered an unknown element in lead ore, found in Mexico. This lead ore is red in color, which he called erythronium, which means red, but 4 years later, scientist named Collet de Sotos claimed that the compound found was lead chromate, which is actually not lead chromate. In 1830, Niels Gabriel Säfström rediscovered the compound in iron ore, due to the colors produced by the unknown. He called it Vanadis, which is a Scandinavian goddess of beauty. Friedrich Wöhler identifies the characteristics of vanadium and erythronium. Roscoe isolated the pure compound back in 1867 by reduction of chloride with hydrogen. Vanadium can be found on the Earth's crust with abundance of 0.0136%, which is the 19th most abundant element in the crust. In terms of transition metals, it is the 5th most abundant and is widely distributed. Vanadium has an atomic number of 23, atomic weight of 50.9415, electronegativity of 1.6, density of 6.11 grams per cubic centimeter, has a melting point of 1915 degrees Celsius and boiling point of 3,350 degrees Celsius. Vanadium has high melting point because the d electrons are inert. Vanadium has 2 naturally occurring isotopes, but it is low in abundance. Vanadium is a shiny metal, which has a body-centered cubic structure. The electrons again contribute on metal-metal bonding, compared with elements on its left side. Vanadium has higher enthalpy of atomization and ionization energy. Vanadium mostly reacts with nonmetals that usually produces non-stoichiometric compounds. At high temperatures, vanadium is also resistant to corrosion due to formation of oxides. However, vanadium can be corroded by hot concentrated mineral acids. The most stable form of vanadium is 4+. Fluorides react with vanadium to give a pentahalide compound. Other vanadium-5 compounds are based on oxohalides and pentoxides. In terms of coordination numbers, vanadium could reach coordination number of 8. Vanadium can also complex with hexacarbonyl, which is unstable. Vanadium-5 oxide forms when vanadium metal is heated. In the presence of excess oxygen, an orange-yellow compound will be yielded. Heating ammonium metavanadate could also yield vanadium-5 oxide. Water and ammonia. The structure of vanadium-5 oxide is quite complicated, but they found that it consists of VO5 that has geometry of trigonal bipyramidal. Vanadium-5 oxide is used as a catalyst, probably because it loses oxygen reversibly when it is heated. It catalyzes the oxidation of sulfur dioxide to sulfur trioxide. Vanadium-5 oxide is amphiprotic, which means that it could act as an acid or base. When dissolved in water, it produces a pale yellow, which is an acidic solution. It reacts with acids in the formation of dioxovanadium-5 ions. Orthovanadated ions could also be formed at high pH. Vanadium-5 oxide is also a mild reducing agent and reduced by acids to form vanadium-4. Reduction with carbon monoxide yields vanadium-2 oxide, which is deep blue in color. Dissolving vanadium-5 oxide in a basic solution and acidified will change its color from orange to red, and it gets darker as the pH reaches 2. Vanadium-5 oxide is hydrated at even lower pH with brown precipitate, and as the pH lowers, a pale yellow solution appears. The site of protonation is oxygen atom. Orthovanadates contain VO4 ions, which is tetrahedral in shape. Pyrovanadates consist of 2 V2O7 ions. Metavanadates, which depend on hydration, NH4VO3, contain infinite number of VO4 and tetrahedral shape, while KVO3, H2O, consists of infinite chains of VO5 units which are trigonal bipyramidal in shape. Crystalline decavanidates are bright orange in color, which is formed in acidic solution. V10O28 is made up of 10 VO6, which is octahedral in shape. Polyanions such as PYH4, V10O28H2, could also be crystallized under the presence of high temperature for several days. NH4VO3 when reacted with ethanol CH2OH3 will yield black crystals of vanadium-4. Vanadium-2 oxide at basic conditions would form crystals of M12V18042H20. The anion consists of VO5, which is square pyramidal as structure in crystallized form of VO2 at basic conditions. They have the ability to enclose negative ions. Polyvanadates with high number of central metal atoms have attained 34 atoms, just as in K10V. 34082 20H20. The geometrical shape could be square pyramidal, tetragonal, trigonal, bipyramidal. For vanadium-5 ions, phosphorus or arsenic, were bonded with oxygen in tetragonal shape, which is capped by two VO groups. Some complex layer sequences form an octahedral and trigonal prismatic. Most of them exhibit conductivity and magnetic properties. Other compounds are easily hydrolyzed, such as NH4, 3VS4, which could be produced by heating of elements under vacuum, which contains tetrahedral VS4 ions. This table shows the halide forms of vanadium. Vanadium is often used as an additive to steel or to make ferrovanadium. The resulting alloy contains about 1–6% vanadium. These are used to make tools, gears, knives, etc. The most useful compound of vanadium is vanadium pentoxide. It is used to fix dyes to fabric, but it is not only limited to that. It can also be used as a catalyst. It is also used in forming superconductive magnets when mixed with gallium.
Vanadium-5 readily reacts with O donors. Hexafluorovanadates are prone to hydrolysis. When vanadate ions are subjected to peroxides, it yields various products depending on pH. For example, in acidic solutions, a red-brown coloration forms as VOO2, 2H2O- and VO2O2, 2H2O3-. At basic solutions, blue-violet crystals such as M3VO2, 4, form. VO2, 4, 3- shows an octahedral arrangement. In oxidation state of 4, common coordination number of vanadium-4 is 6. VF4 pounds is insoluble in organic solvents. VCl4- is paramagnetic with 6 coordinate monomers. High coordination numbers for vanadium are also found. VO2+ ions are the most commonly studied for vanadium-4. VO2+ forms stable compounds with halides and N-ligands except I-. They form blue to green color. They are commonly a 5 coordination number with square pyramidal as arrangement. Some VO2+ ions also form as distorted octahedral arrangement. In oxidation state of 3, VCl3 is preferably used to produce vanadium-3. Usually VCl3 is reduced. Vanadium-3 forms an octahedral arrangement. VX6, 3-, VX5L2-, VX4L2- and neutral, VX3 pounds, 3, are common. Tetrahedral arrangement like VCl4- and VBr4- also exists. Trigonal bipyramidal like VX3, NMe3, 2, and VNSIMe3, 2, 3 in trigonal planar also forms. The highest coordination number that vanadium can attain is 7 with a pentagonal bipyramidal structure. Example of which is K4, VCN7, 2H2O. In oxidation state of 2, they are prepared by reduction with zinc in acidic solutions. Several salts like VH2O, 6, 2 plus and VCl2 pounds, 4, with N oral ligands attached to vanadium. These salts can be distinguished by their colors like VCl2 pounds, 4, which forms a green color. The longest ligand chain that can be prepared is V3, Raku, 6, Me2 and CHCHNME2, 2. The central atom is held by carbazylate bridges.